Okay, I think the record is now on. So we are back to this example. And this is where we were before the long break, because we had an extra holiday and then some grand break. So we skipped like 2 weeks in a row. Okay, so here we are. We have the trust now, and looks like this. Now let me remind you guys quickly. This is not a very good example because it has, so it's not a bad example, but it's not, say, very demonstrative of some point. That is, it has 1, 2, 3, and 4 degree of freedom here, which incidentally, they are the same as the degree of freedom of the member. So when the degree of freedom of the system happens to be equal to the degree of freedom of the member, you don't see very well that you actually can have the stiffness matrix that with the size related to the degree of freedom of the entire system. Okay, that's just one point that we missed from this example. And we have done the numbering. So we call this the Q1, Q2, Q3, and then Q4. We have given all the members the numbers and local nodes. So this is your member number 1. This is local node 1 and 2. So that means the code matrix for this one, this is 1, this is 2, right? And we have Q3 here in X direction. So our code for member number 1 is now 3, 0, 1, and 2. For member number 2, this is local node 1, and then this is local node 2. So we have 0, 0 here, see? And then local node 2, we have 1 and 2. For member number 3, this is local node 1 and 2. So we have at local node 1, it's 4, 0, and then go to 1, 2. For member number 4, we have local node 1, 2 like this. So at local node 1, we have 3. At local node 2, we have 4. So it becomes 3, 0, 4, 0, 0, because we don't have displacement in Y direction. And likewise for member number 5, we have the hinge on the right side. So we only have 1 displacement Q4. So it's 4, 0, 0, 0, 0. Okay. So far, you guys are okay? You know, funny thing is that I posted in the wrong group. So I thought that I already informed you to review the material like a few days ago, but I posted in the wrong group. Pathetic, really. But it happens, you know. Okay. We're going to begin now. All right. So the local node is 1, 2. It's very important in a sense that it's going to give you the orientation of the member. Okay. Let's say you look at member number 1 here. Now local node is 1, 2. So when you look at member number 1, what you are going to see is like this. And your vector always points from 1 to 2. So if we give local node 1, 2 like this, this is your vector. Okay. And the trigonometry system that we use, of course, it's a normal system. And when you have your member number 1 like this, this becomes your orientation. You see that? But let's suppose I switch the local node. Let's say if I do this, 1 here and 2 here. The difference is that now your member number 1 vector is going to point to quadrant number 3. You see that? And here is your origin. And therefore your orientation becomes this instead. Okay. Well, this might not, for this particular member, it may not be much because quadrant 1, the sine is positive, the cosine is positive. And for quadrant 3, sine is negative and cosine is negative. Okay. But for, say, member number 2, you know, this one, the direction of the member or the orientation will affect your calculation somewhat. Okay, and up to this point, some students cannot work on trigonometry, which is very, very sad. The basic trigonometry that you use should be, you know, the ones that you've learned since junior high school. And to think that you are in the university studying engineering and you still mess this up is such a mess. And believe me, some will. And notice that here, you see, this is theta, right? And now you must know that this is the same, correct? So you should be able to work this out. So let's move on and look at the member number 1. Okay. Now this is not what we're going to do. This is for demonstration. Okay. So we're going to look at member number 1 with local node 1, 2, just like that. So let's see. Here is local node 1, 2. Okay. So that means this is the orientation of your member, and that is the theta. Okay. Now, oh, I don't have you. Okay. That's 3, 4, 5. So it's a famous 3, 4, 5 triangle. Okay. 3 and 4 and 5. You can see from now that the sine is 4/5 and the cosine is therefore 3/5. Okay. We can work some constant out, the EA over L term. E is 2 million, I suppose. Yeah. A for this member is 85. It's in the square centimeter, and L, that's 5 meters, right? But I prefer to use the same unit, so it's 5 multiplied by 100. So here the constant is 34 multiplied by 10 to the power of 4. Okay. So now, if you cannot recall, I should maybe put the formula here somewhere. It's I don't know. Hang on a minute. But you guys can open up the page and see it. Why is this here? I don't know. I misplaced something. Yeah. 1 moment, please. Yeah, it's actually I can remember, but just to be sure, sine, cosine, and sine squared. Okay, that's a formula, and you should notice that this is broken into 4 quadrants. This guy is positive, just like that one, and that is negative and negative. So with that, we can now work on the stiffness of member number 1. So let's say K1, okay, is going to be 34 10 to the power of 4. But you know, you have cosine square. Cosine square is going to be 9 over 25, right? Can you see that? Cosine square is 9 over 25, and sine square is going to be 16 over 25, and sine cosine is 12 over 25. So with that, I am taking 25 out. Okay. And the cosine square, that's 9. Sine is 16. and something in between is 12. You do it like this, you should not get it wrong, you know what I mean? And see, that's one quadrant done. So here is 9, 12, 12, and 16. And the rest will be the negative ones. See how easy that is? Minus 9, minus 12, minus 12, and minus 16. And here's minus 9, minus 12, minus 12, and minus 16. Okay? And we have the code here, which maybe I can change the color a little bit so that you know, sorry. What is this? So that we are aware of this. Okay, so the code is green. For member number 1, here is our code, right? 3012. Now you can impose the code here. 3, 0, 1, and 2. Okay, you can choose to do this right away. Let me show it to you right now. Okay, because I think it's a better way if you can shuffle this into the 4x4, which it's just the metrics for the global system of the entire structure. Okay, that's why I don't like this example. It doesn't show that it should turn into the metrics with the same size as the unknowns of the structure of the entire structure. Okay, but anyway, here, okay, something up front is going to be the same. So let me write down 34 multiplied by 10 to the power of 4. Then that's 25. So now we're going to shuffle this. Okay, 3. That, oops, I should write it in both directions. 3, 0, 1, 2. You can cross out the line 0 right away. Not going to be involved. And then you see here's a group of 1, 2, right? So you can place them just like that. Group of 1, 2. So it's 9, 12, 12, and 16. Okay. And then you can look at this is row 3. And then that's 1, that's 2, and that's 3. So it's minus 9, minus 12, and then 9. And then 9. But I forgot this as well. So let's go back. Row 1, that's 9 and 12. And then at column 3, I also have minus 9. And for row 2, it's 12, 16, and minus 12. So minus 9 and minus 12. Minus 9 and minus 12, you see? And the contribution from member number 1 is just for 3 by 3. So the rest has to be 0, right? So that is the matrix that is pretty ready to be assembled into the global stiffness system, or the global stiffness matrix of the entire system. Okay, so after you've done this yourself, you can actually use your calculator to memorize this entire matrix. Okay, and then you do this for the rest of the members, and then after you have give this input for your calculator, you can just add them up later. It's very easy, but don't forget that you have the coefficient up front as well. So okay, up to this point, any question for member number 1? Any question? I think it's pretty straightforward, and those of you who somehow manage to mess this up, fingers crossed, no one will. You feel very sorry because it's just pretty easy. And I think you feel like anyone can do it. So now member number 2. Member number 2, I hope you can see it from your say notes. it's like this. And the orientation is like this, correct? So that is your theta. And then again, the sine and cosine will be based on this angle. Can't believe that somebody will mess this up. And you see the vector here points into the second quadrant, correct? So that means the sine is positive, but the cosine is going to be negative, correct? And in fact, it's a similar angle as that of member number one. It's just the sine is different because of the orientation. So sine is 450, but the cosine is minus 350 this time. And sine square is, again, as before, 16 over 25. Cosine square is positive because it's negative, multiplied by negative, right? Okay. And the coefficient is similar to that of member number one because it has the same cross section, it has the same length. So I'm just going to go over here and write K2 now. So that's going to be 34 multiplied by 10 to the power of 4 over 25. 25 is due to the trigonometry. I bring it out of the matrix, okay? Because I'm too lazy, right? So now cosine square is 9, but sine cosine is minus 12. Correct? Because your sine is positive, but your cosine is negative. That is minus 12. Here is 16. So after you finish one quadrant, you know that it's going to be similar to the quadrant 1 is quadrant 4. So it's 9 minus 12, and then 16. Okay, these two quadrants are similar. And then the rest is just, you know, the opposite sign convention. So it becomes minus 9, 12, 12, minus 16, minus 9, 12, 12, and minus 16. Okay, I think I place it too close to the top. So I'm just going to have to move this a little bit because I plan to impose the code on it. You can just go back and look, and now you know that the code for member number 2 is 0012. So it's 0012, 0012. So you can eliminate anything that has 0 on it. So the contribution to the global stiffness metrics of the entire structure or the entire system, it's just this quadrant. You can see that now, right? Trying to help. Okay, so that's okay. So we can rewrite this into this. What color did I use? Okay, same. So here is nine minus 12, and then 16. And the rest is 0, right? That's it for member number 2. Is there any question? If there is any question, we move on to member number 3. Well, that one is the easy one, right? But don't mess up your sign or your orientation. That is our orientation, okay? So it's going like this. So that means sine is 1, cosine is 0, right? And this guy has a different cross section, so we have to calculate EA over L term bit. That's going to be 2 million. A is now 65, and the length is 4 meters, I suppose. Am I right? Yeah. And multiply by 100. But let me move this up so that I can write the matrix down there. Oops. Here is equal to 32.5 multiplied by 10 to the power of 4. So K for member number 3, that's going to be 32.5 multiplied by 10 to the power of 4. Now I have this. Cosine square is 0, right? Sine cosine is 0, 0, and sine square is 1. So that's all we have. And then, you know, the rest is similar. Not the rest, I'm sorry. Quadrant 4 is similar. So it's 0, 0, 0, and 1. And now these remaining 2 quadrants will be opposite in terms of sign convention. 0, 0, 0, minus 1, 0, 0, 0, minus 1. Okay? See, it's not that difficult. You just have to have a good concentration while you're doing it. And of course, that means you understand how things are going as well. Just too close to the top. Okay. This guy goes back. So now I'm going to impose the code. That's going to be 4, 0, 1, 2. 4, 0, 1, 2. So, you know, that's where your concentration would begin, because now you need to know that there are some zeros because there are zeros, and there are some zeros because, you know, they don't have the contribution. Okay, I think I'm gonna have to use a color that is more, say, distinctive. Maybe this guy. So we take this out, and we take that out. And now we know here, let's go to quadrant 1, 2, right? And then 4. So here, this is going to become 32.5 multiplied by 10 to the power of 4. And the matrix, that's 1, 2, 0, 0, 0, 1. And then in 3, we don't have anything, right? We don't have row 3, we don't have column 3. So we don't have row 3. I can just write them down like this. And we don't have column 3. So these are rows because we don't have the contribution, right? And then you can see row 1, column 1, 2, there's nothing in 3, and then 4, which is also 0. Okay? And then row 2, column 1, 2, it's 0, 1, 0, 1. Nothing in row 3, and then row 4 is also 0. And then the last one, row 4, 1 and 2 are also 0. And then in 4, that's also 0. So we end up having something like that. You see, in the end, it's just 1. Say, coordinate in the matrix that has the value. So that's member number 3. You want to have a minute to take notes with this one? I don't know if this is going to help better. See, that's the same, right? It comes in here. And then that's the one, that's the one, and that's the one, that's the one, that's the one. Do you need a minute to take the notes, or you don't? Hello, anyone?
Oh, I can catch up.
You can catch up. Otherwise, you become catch up, right? That's a joke because say the mother tomato is telling her, say, baby tomato just to catch up. Otherwise, if we roadkill, become ketchup, something like that. Anyway, if you can catch up, what about others? No one is talking. So I think I'm gonna progress slowly to member number 4 and 5, which incidentally, they are the same. Okay, 4 and 5. We have this. Okay, and the orientation is simple. Now you see, you can give any local node number any way you want, but it's gonna affect your orientation. So let's say before I do 4 or 5, let me go back to number 3, for example. You can say, okay, this is my local node 1, this is my local node 2. So you're gonna end up with a simple trigonometry. But let's say someone, okay, I want to do this as 1 and 2. If you change something, say, if you do this local node 1 and 2, you must know that your orientation is like this. And your sine is now -1 and cosine remains 0. So that's how things get affected. And now you can see your code. How easy your work is will depend on how you give the Q1, Q2, Q3, and Q4 to your system as well. If you mess things up, like here's my Q1, here's my Q2, here's my Q3, here's my Q4, you know, when you're trying to assemble the metrics, it's gonna be quite a mess. So smart people who plan ahead and try to choose the easiest way that has, say, the least number of chances for you to make mistakes. So then again, you may question, how am I supposed to know things like this? You know, how am I supposed to know which numbering I should use to make my life easier? So you know what the answer is? The answer is in the practice. You need to do some work, and then you will recognize yourself that, okay, doing this will give you the easier life. But if you don't practice and you pray for the miracle to happen in the exam, well, I'm sorry, life doesn't work that way. Okay, so let's say now we go back to 4 and 5, and local node 1, 2 is like this. So it's pretty simple. The orientation is like this. So sine is 0, cosine is 1. Okay, because that's your orientation is 0 degree. Okay, and we need to do some calculation for EA over L for member 4, 5. That's 2 million. A is 65. L is now 3 meters. Okay. Here will turn out to be 3.3 multiplied by 10,000. Okay. So for K4, that's going to be 43.3 multiplied by that. And now is 1000, right? Now you know quadrant 1 and 4. 1000. And then the two remaining quadrants, similar number but opposite signs, and becomes -1 0 0 0 -1 0 0 0. Okay, and 4 and 5, they are going to be similar. So let me copy this. Okay, Now I'm just gonna put the code on. For 4, that's gonna be 3040 3040. So yeah, we can eliminate some like this. Oh, interesting, right? You see, now you have all the values. This guy will come out to be like this. You have 3 and 4, see? So basically, this gives you 1, -1, -1, and 1. The rest is 0, right? Are you still with me?
Yes, yes.
Okay, just you. What about the rest? We have 8 students today. A few.
Yes ค่ะ
Yes, thank you. One lady. Or two ladies actually. Okay, thank you. Anyway, so code for member, I should erase this one and turn it into 5, right? Yeah. So here the code is 4000 4000. So pretty easy. Okay. We actually, instead of chalking off things that I don't use, that's just one term that I have. That's the one. Okay. So see, it becomes 43.3 multiplied by 10 to the power of 4. And this time, everything is 0 except this term, right? The rest is 0. So now, you see, now we have everything. So I can just line them up. Let me try. Hope that I will succeed. Okay. See, the size are not the same. But that's not, remember the stiffness matrix of member number 1 ready to be assembled. Okay. Race with me. No, you know that's the name of the song, but we'll talk about that later. Copy this. Let's hope I can pull this off. Paste it. Okay, so that's member number 1. Okay. Oops. Okay. That's member number 2. Ooh, sorry, too big. Maybe I should, you know what? Hang on. Can I resize this? Of course I can. But, let's resize. Okay. I should resize the second one first, right? I don't have to choose this again. Anyway, it's done. Okay, it doesn't look so bad after all. Plus this, okay. Now, that's 3. It's a bit of a mess. How can I erase that? Oh, please. Okay. But I'm gonna have to erase this first. Okay. Add this. add 4 and 5, which are here. Okay, we're almost done. So hang in there. Okay. Okay, and then the last one. Oops, let's do it first. We're nearly there. Okay, copy, paste. Okay, so you get the idea. Okay. Now, the reason I'm doing this is I just want you to feel that if you arrange all the numbers in the matrix into this kind of form, you can, as I said earlier, you can put this in your calculator. You know, you can use the memory of calculator in the matrix and say, okay, this is matrix A, this is matrix B, this is matrix C, D, and E. And then you can use the simple arithmetics to add them up. So it's going to be something like, you know, 34 multiplied by this over 25A plus the same. Just be careful of the coefficient because many times they're not the same. Over 25, then multiply by B and so on. You can use a calculator to do it. Okay, that's what I do, you know. And one more thing I want you to notice is that you look at matrix of member number 1 here. It's symmetric, isn't it? And this is your line of symmetry. You see, it's always the diagonal line here. The matrix, the stiffness matrix for member number 1 is symmetric. For member number 2 is symmetric. And likewise for every member. You see, can you notice that? Every matrix is symmetric. So once you add them all up, the stiffness matrix of the system should remain symmetric. Am I correct or not?
Yes, yes.
Yes. So that means after you assemble everything, you can check your results by looking at the axis of symmetry and see if you still have that. If you don't, it means that you have committed simple mistakes in arithmetics. Okay, and you can always check that, you know, and go back and fix it. Okay, so now before we have a break, I can give you this. So in the end, after I add them up, maybe, you know, I should give you some name. This is step that we, I have the step number. Okay, so let me go back there. Maybe giving you some steps would ease the pain. This is step number 1. I call it numbering. From this on, this is step number 2 and 3. It's element stiffness matrix. Or you can say member stiffness matrix. Okay. I guess that's this is step number 2. Oops, sorry. This is step number 2, and this is step number 3. You know, all together. So here, oops, sorry. This is step number 4, assembly. Okay. So in the end, we have the results, folks. Here. So I'm taking 10 to the power 4 outside. So this is the stiffness matrix of our system now. Okay. I'm taking this outside and I put the coefficients inside. So see some strange numbers. 24.5. Be careful of your significant figures. 0, 0. Minus 12.2. You know what? Let me be crazy about this a little bit, because you see how the numbers are double. This 24.48. It's 12.24. 0, 76 minus 16.3, 0. And you expect that because that is that. So yeah, it's minus 12.24. Here is, yeah, the same, minus 16.3. Let me move it a little bit so that you see things better. Okay. Now it is, you know, in the live symmetry, you expect to get it right because there's no help. 55.6 minus 43.3. And let me expand that a little bit. Okay, here it must be 0. Yes, here it must be 0. Here it must be minus 43.3. And here's a number that you must get. It's 82.7. Okay. That is the stiffness matrix of the system. Okay. I think it's 10:20. I actually started off a little bit late, but it's okay. I think we have plenty of time to finish everything before the exam. So let us take a break. Is there any question? Pretty straightforward, you know. Question, please.
Not yet.
Okay, it's so clear, right? So let me okay, this number 25 actually comes from the denominator in here. Okay, you see, remember?
Yes.
Here it's pretty incumbent to write everything. The sine is 4/5, so the sine square is 16/25. Cosine 3/5, cosine square is 9/25, and sine cosine is going to be 12/25. Okay, so instead of writing 25 for every term in the matrix here, I just pull it out.
Oh.
That's all.
Oh, okay.
Missed it because we went a little bit quickly. So we only have 25 for the first two because the sine cosine has some numbers.
Okay, I understand.
Okay? Yeah, so for member 2, you see we have 4/5 and minus 3/5. But for member 3, 4, and 5, it's just 1 and 0. Good.
Okay, I get it.
You see, it doesn't hurt to ask questions, even if you miss some simple things like this. The best thing is not to leave anything unturned. Okay, because for example, some of you struggle because somehow you cannot keep good concentration. It's not because you don't understand things. And I think when I used to have a debate with some of ajahns, you know, see, knowledge is important, okay? Ability is important, but what you cannot lack in engineering work is precision and accuracy. Not only that you know stuff, you understand stuff, you must be able to carry out your work accurately as well, right? You know everything, but you cannot perform your calculation up until the end to get the right numbers. So you're going to mess up your work along the line. And sometimes luck, not sometimes, luck has nothing to do with it. We practice so that we become accurate. Okay, guys? Is there any more questions?